Hey y'all, here is a look at number 6, the revolutionary solid problem and some help. I'm going to go pretty quickly through it, but you can pause and do that stuff. And thank you to you guys who are so kind and brave enough to email and say, Mr. Seeley, I think you got it wrong when you were in class, because I totally did. I blew it. You have to please forgive me. When I was talking about that, rotating the arc length and getting the volume of it, I think some of you were making some noise in the back, like you didn't think that was right, or I heard somewhere in the midst of it, will you make that louder? Because sometimes when I bark these things and I'm on a roll and I'm excited, I get excited about this stuff. I'll bark things out of tune, and it's just my enthusiasm comes overcomes my filter, and I'm connecting things in my brain at that moment, sometimes in real time, that just aren't right. So if you see something that comes up, just let me know. But I know better when I sit down and think a little bit harder. I'm like, oh, well, that's silly enough. Why did I do that? There's a formula for it, and my memory is terrible. It's one of my downfalls as well. But this is the actual thing. If you pull it up, it's the easiest thing to run with. And I'll show you where it comes from. Now that we got a minute, that's the that's the surface area if you take it around the y-axis. So maybe we should call this the SA axis. That'll do. Surface area of a rotational solid around the y-axis has that dy designation, and you'll notice it has 2 pi in it. And then the addition it's basically arc length width, that gy that shows up in there. And there's a reason for that. And then I'll show that here in just a second, just for the sake of it, in case you get another example that's maybe around the x-axis or something. It would just change the function to be in terms of x, and then this would be a derivative would be dy dx instead of dx dy squared. I'll show you what that means as well. So that would mean surface area of a rotational solid around the y-axis. There we go. That's the one I want. And even in these videos, if I say something as I'm just talking along, you see something that's wrong, do please, as many of you, actually several of you did very kindly, as you said, Mr. Seeley, I don't think it's quite right. And man, it makes my day. You won't make me feel bad at all. You'll make me feel a lot better if you said something. The problem at hand looks like we've got an x equals y nice curve. We would call that g of y. So I'm actually going to say, hey, that curve I've got there in number 6, I hope you can see it on my screen clearly. Looks like you can. G of y equals that 3x to the 1/2 minus 1/2 to the 3/2. And that 1/2 to the 3/2 is kind of a distractor. It's just a constant. And when we take the derivative, it's going to go away. I think it's there to make you think of something and throw you off. Who knows? In short, your formula will be 2 pi. And you'll put in the g of y function, which is right here. And then you'll take it times the arc length, kind of as you normally would for this problem. And just for those who need to know where this comes from, because I'm all reminded of things once I think of where they come from, and life is better in my brain. But the derivative of that is rather simple. I'm going to put it up above so you can see it. If you notice that x, or I should, that's right, I think I made that an x. It shouldn't be an x. It's a y. But when you take the derivative of that in terms of y, that 3y to the 1/2 becomes 3/2 y to the negative 1/2. And the other constant just goes away. That's it. That's our derivative. Nothing more than that. So that's what you'll see inside the parentheses here, 3y to the negative 1/2. And that, of course, gets squared, and then we're done with the dy. Integrate that on the appropriate interval. Mine, I believe, is it 1 to 3? 1 to 5. So we go from 1 to 5, and you can use your calculator. You get that. That's it. That's all the formula is. Just be extra careful with parentheses and things like that. Quick run through of where this formula comes from, in case you're interested. This particular graph, the y to the 1/2, x equals y to the 1/2 is kind of one side of a parabola. And this is poorly drawn. We're rotating the whole thing, and so we're getting kind of I want to know the surface area of the outside of this. Maybe it's kind of the top of a wine glass or something like that has a stem, but that's the outside. Its surface area would be kind of akin to how we do a cylinder in its outer edge, if you want to do the surface area on that. So here's my cylinder, my little can, and if I think of the outside edge, if I paint it nice and green, it is the same as, if I unroll that can, it's that whole surface area of that unrolled piece. Now, when I unroll the can, the top edge here is the circumference. You see becomes 2 pi times whatever my radius is for this particular can. So 2 pi times a radius, which we'll give a function name to here in a minute. And then there's a height component. So from here to here, there's a height. And we see that also as the same height over in my rectangular unfolded piece. Now, how's that compare to our little vase over here? Well, the height piece, I'm going to do some highlighting in various colors and see if this gives you some sense of it. Let's go with, I don't know, red. How to stand out, right? Here's this outer edge here is kind of akin to the height that we get right there. So that function, if you think of its arc length along there, there is a height component. There's a 2 pi, there's a radius in here, kind of like the radius that's inside there. Well, the cylinder has a constant radius, so we should just put a number in there, where ours has a variant radius depending on where you are in there. Well, our variant radius is that shortening distance x to the edge of our curve. It's our function x equals, 3 halves, 3y to the 1/2 minus 1/2 to the 3 halves power. So that's what that whole function is, our radius. I'm going to plug that in here. So here's our function, 3y to the 1/2 minus, isn't it 1/2 to the 3 halves or something like that? Okay, there's our function that goes in there. That's the radius of our particular graph. And then the height, instead of being a constant, consistent height, our height is kind of the length of that whole side piece, and that becomes right here. And that's the arc length of that piece. Well, it's more or less of an arc length and more of a distance formula for our particular graph. So it's a similar idea, and that's, if you want to get into the derivation of it, you can. But that's kind of the idea, is that it's just the distance formula that takes you along there at a limited value, so you do an infinite number of them. So when we get done putting it all together, the surface area of this is these two multiplied together, which looks a lot like what we've got going up here, including the 2 pi. Cool. So I happen to have something similar to this going up on GeoGebra because somebody sent me their example and I started working it. So if you're willing, I'm going to go over to that one. Here we go. So I'll just use this example. Let's see if I've got it up here. Here's a function, 3x to the 1/2. Ours slightly different. It's 3. Oh, by the way, I'm going to write it in terms of x just because the integration on the GeoGebra is a little easier. So these x's you're seeing right here, think of them as y's. It was just easier to type it in if I do it that way. So 3x to the 1/2, does that match? And 1/2, is that right? You double check what ours is. Yeah, 1/2 to the 3 halves. Okay, let's do it. So instead of 1/4, it'll be 1/2 inside my function here. So I can get that to happen, bingo. And h of x then, or f of x down below here. Oh, I extended it. This is like the arc length thing that goes inside there. I was just having some fun. Looks like our derivative would be the same, 3 halves y to the negative 1/2. Bingo, squared. Cool. And so down below, what's interesting is I actually did a couple of things. I actually did the arc length of our function f here. Here's just the arc length of our given function. Right inside here, all it is the derivative right here, squared under the radical 2 pi. And then if you notice right here, I have, maybe I can type on this a little bit. Here, double click on it. Does it show anymore? No, it just says integral of f on the interval 1 to 5, and it gave me a result. There's my arc length. Now, if I want the outside surface area, here it is. I had to multiply the original function times the arc length function here, and then do the integral on 1 to 5. And assuming all is well in my typing, it looks like 167.37. Now I'm going to type that in here. You have to go to 3 decimal places, and I'll show you what happens. 167.37. I've got to fix my GeoGebra settings to be 3 decimal places. And somewhere in here, I've got some settings where I can mess with that stuff right here in options and stuff. I didn't take time to do that yet. So when I type this in, it's going to be wrong for a moment, but watch, it'll give me the correct answer, which is essentially the same. Okay, fine, check your answer. Yep, fine, I like what I got. Final check, blah, blah, blah. Okay, there it is. There's a rounding error and a little funkiness that's going on inside there. I think I even did the wrong interval on the one I had there. But my, yeah, I think I put my endpoints are 1 and 3 or something. But we got to fix it doesn't round appropriately, so I got to go back and fix that on top of there. Okay, so here, let's go back and get our 159-ish, because I think I mistyped something on there. Here, whoops, the daisy. Can I find you? There, little buddy. And got it. Integral 1 to 5, f of g, h of x times f of x. Yeah, 3x to the 1/2 minus 1/2. Oh, it is 1/2. Did I mistype it? Maybe I had it right the first time. Yep, there you go. So if you type those in there. But that's just so you know that GeoGebra, if you get interested in using that particular software, I'll let you go. There's our 159.49. So there you go. So I've got this set up. so that it'll do that for you. If you're interested in knowing how to do this, that's the other reason I brought this up, I'll send you this file and I'll email it out and say, hey, if you want to try and see how this integration stuff goes with it, you can, and have fun. Talk to you soon.